Welcome back, and to this second session this week, where the aim is to discuss in more detail Wick's theorem. I postponed one of the topics from yesterday about the diagrammatic representation. This is something which I will discuss in more detail today. But today we are going to prove Wick's theorem, and then we are going to implement this with specific examples. Now, if you go through the slides which we have, there is some material which we decided, how to say, not to cover when we do things on the whiteboard. And this is material which we would like you to read a little bit more about. And these are just simply manipulations where you use the spectral decomposition of an operator. And with the spectral decomposition acting on a given Slater determinant, you can then set up the action without the permutation of any particle pair or any possible permutations. Then you can interchange particle 1 and 2, and then you can continue by computing all possible permutations as we discussed with the setup of a determinant. And when you do that, you arrive at a compact expression for a one-body operator in second quantization, which is now given by an integral, which we leave undefined. And in some cases, this this single particle basis, so alpha and beta is a single particle basis. We can assume that that is an orthonormal basis, which is also an eigenbasis for H0. Which means again that the integral becomes just a eigenvalue or transforms into an eigenvalue where alpha has to be equal to beta. And then that double sum reduces to a single sum. So that's one possibility, or we can just keep it as it stands. And then it would represent a transition from a state beta to a state alpha. That's the way you would read that constant term which we have here, this one. And we discussed that in connection with the calculation of the energy of a system. And in many implementations, we will often assume that we have an orthonormal basis, which is an eigenbasis of this part of the Hamiltonian, H0. And then we can do the same thing. We had an exercise as an example yesterday where we went through everything by using the contractions and the anti-commutation rules. And then we can find, for at least for one state, in a pretty simple way, we can find the expression for the energy, and then we get the expression as expected. Then we can repeat a similar rewrite of the two-body operator, where we have a two-body operator in what we normally would call loosely the first quantization or the coordinate space representation. And then this one is transformed into the second quantized form, which then becomes equal. And this again is something which I invite you to take a look at these derivations. And we can actually, due to the anti-symmetry here, if you look at the matrix elements, it goes like alpha, beta, gamma, delta, or integrals, which is a more correct name. We often end up calling this for matrix elements. But in strictly speaking, this is an integral over 2 degrees of freedom, x1 and x2, or xi and xj. And in this case, what you see here is that these two operators have an interchange position, and that follows from the manipulations before, and is due to the fact that you're dealing with fermions and have to obey the anti-symmetry. So the form of a two-body operator looks like this. It doesn't need to be something which represents a potential energy or an interaction between two particles. This could be an operator. If you're doing, let's say, nuclear physics, there is a very important process which is called double beta decay, which is a very rare process people are looking after. And you can have a double beta decay or nucleus with and without neutrino emission. And that is given by a two-body operator, which comes from electroweak theory. And that would be an example where you would replace this quantity V here with another type of operator. So these are the kind of forms which we will deal mainly with in this course. And then what we are going to do now, I'm going to switch immediately back to the whiteboard, and we are going to look at some examples, but then we're also going to prove Wick's theorem. And just let me quickly remind you, just go through these ones and say something about Wick's theorem. So one of the things which we are doing then is that we have a chain of operators, and we introduced yesterday something we call normal ordering and contractions. So let's repeat these elements, and then we're going to restate Wick's theorem, and then we're going to prove it. So let's do that. And this plays a fundamental role in many-body physics because it simplifies to a huge extent the bookkeeping in running calculations. And one of the calculations which you can see is the expectation value of this quantity here, where you have a two-body state and then another two-body state in the brass state. So you make a transition due to the interaction from a two-body state with beta 1, beta 2 as quantum numbers, and you end in a new state alpha 1, alpha 2. And the example here would just be a set of operations where you're simply using the anti-commutation rules. So doing a two-body operator, which involves two creation and two annihilation operators on a two-body state, and calculating a transition probability for that, means that you will have 4 creation operators and 4 annihilation operators. And if you do all the contractions, you can just think yourself of the amount of boring labor which you have to do, and bookkeeping, not the least. Because it's pretty easy when you do all these kind of contractions with the operator so that you move. The whole idea then is actually to move operators so that you will have an annihilation operator to the right, acting on the vacuum. And doing this repeatedly is not an exciting thing to do. It's prone to errors. When I did this the first time, I had 3-4 sheets of papers, and I never got the result I should get. And there's always some kind of minus sign or plus sign which you miss somewhere. There's some indices which are interchanged. So doing this in this, what I would call the brute force way with the anti-commutation rules, is something which we can simplify considerably when we use Wick's theorem. So the whole thing here is that you can do this, and if you venture beyond a two-body state and you do a three-body state, it's not getting fun. And this is where Wick's theorem comes to our rescue as a very compact way of calculating these type of expectation values and transition probabilities. So let's take a look now at some of the quantities which we discussed yesterday, and try to remind ourselves about some of these technicalities before we look at some more examples and prove Wick's theorem. So one of the things which we introduced yesterday, some of the basic concepts, is that of contractions and normal ordering. So when you're looking at an expectation value like this, not that one, it should be, just a moment, that one. If we look at this expectation value here, we redefine that one in terms of using the anti-commutation rules. So we have a delta, alpha, beta, and then we get minus, and then we have 0 of A beta. And this is what we call normal ordered, so that you have all the creation operators to the left and annihilation to the right. And we know that this is exactly equal to 0. This term here is a term which is equal to actually that expectation value. And we label that one in terms of a so-called contraction. So the Kronecker delta is given by this symbol, which we call a contraction. And this term here is something which we rewrite as the normal order product of the operators A alpha, A beta. So the minus sign comes from our usage of the anti-commutation rules, but we write this in a more compact form as a normal product plus a specific contraction. What you will see this rewritten as, and this is actually Wick's theorem for two operators, one creation and one annihilation. If I have only one operator here, just one, then we know immediately that that has to be zero from the definition of the annihilation and creation operators. And if we have only a creation operator, so having an odd number of creation and annihilation operators gives us zero. So what we did yesterday then was actually to look at the preliminary version of Wick's theorem. So when we have two operators, what we have then is that we can rewrite an expectation value. And now let's call X and Y for two different operators. It can be creation and annihilation. And this is something which we can now write as N, and then we have the normal order product, which is the last term you see here, plus the sum over all possible contractions between the two operators. And that means that we would write that as a normal order product of X, Y, but then contracted. So that quantity there is actually the quantity which corresponds to 0, X, Y, 0. And that's one contraction. So X and Y could be a chain of operators, then we have to be careful. But if X is just an annihilation operator and Y is a creation operator, then it's exactly the same as we have here. So this is the first step in showing Wick's theorem. So we can actually show this for 2, 3, and 4 operators. And then the whole idea is by induction to show that this applies to any number of operators. So let me also remind you of some of the expressions which we put up last time. So before we move on now, it's useful to look at or remind ourselves of the following contractions. So this one is the only one which is non-zero. So that's the Kronecker delta. Then if we try to take the contraction between A alpha dagger, A beta, like this is exactly equal to 0. Because what it means is that we are trying to calculate this expectation value here. And we know that when A B alpha and A beta acts on 0, this is exactly equal to 0. So this is by definition from the operators. This is a quantity which we define to be 0. And the same thing applies to this contraction here between two creation operators and two annihilation operators. This is also equal to 0. So the contraction means simply that we set up this expectation value, vacuum to vacuum expectation values between two operators. Okay? So these are going to be the kind of driving rules which we now implement for more complicated cases. The thing which we went through yesterday was the next example where we have N equal 3 operators. And the only case which we had to consider was the case where we could have 2 of the operators being a creation operator and 1 being annihilation, or vice versa. If we have 3 creation operators or 3 annihilation operators, it's automatically 0 due to the property which we have defined here. So when you have the same type of operators, this is automatically equal to 0 here. So let me just bring back my notes here and set up the case which we went through yesterday with 3 operators. And the example which we looked at then was an expectation value of 0, A1, A2, A3 dagger. That was the example we went through. And we could rewrite that one as the normal order product of these operators, A1, A2, A3 dagger, plus a normal order product where we have performed a contraction between one pair. So we have this pair here, which is non-zero. You can obviously set up all the possible contractions, but if I do a contraction between A1 and A2, that is automatically zero. So I'm setting up those contractions which are non-zero, only those. So when you're using Wick's theorem, there is no point in going through all these guys which give you zero. So we had a final term here, which was A1, A2, A3 dagger, like that. Now, what happens when we perform the contraction is that this term gives us obviously delta 2, 3, but then we have an A1, and that operator gives us zero. So all the normal order products where one operator or more operators are left uncontracted gives automatically zero. So that's a pretty simple rule. And you see also from this case that if you don't have an equal number of pairs of creation and annihilation operators, when you look at an expression, then you can just read off immediately that this has to be zero. So then there's no point in doing any calculation. Now, the next case which we did, so you see now again that this is looking like a precursor to what we will call the full Wick's theorem. And the final case which we looked at yesterday was the case with n equal to 4. And then we were looking at the expectation value of A1, A2, A3, and A4. And we went in a very slavish manner. We went through all the possible combinations we could get by using the anti-commutation rules. Now, that's a pretty boring exercise, and this is where actually Wick's theorem comes to our rescue. So what we found then yesterday, when we did all these operations, was that we had now a normal order product, an expectation value, which is automatically zero. So you don't need to do anything when you look at this quantity here, because then we have normal ordered it, and then we will be having annihilation operators acting on a true vacuum, which gives us zero. And then we have the set of all possible one contractions. So we have 1, A2, A3, and we leave out the contractions with the same type of operators. So that is one possible contraction. And obviously, when I normal ordered this quantity, I will have A1 acting on the true vacuum, which gives us zero. So this is a term we don't need to do anything with. And when we did this exercise, which was not so exciting, I just wanted to repeat it so that we can jump into Wick's theorem. So we could have this contraction here. We got a new set where we had an n of A1, A2, A3, and A4. So we have this contraction, and then we had a new one. And then we have an A1, A2, and the final one here would be now A1 going, or A2 going to A4. And then we had the two cases where these operators are fully contracted. So we have this case and that one, plus an n of A1, A2, A3 dagger, A4, and then we contract this one with that one. So what we have here, the first terms, this one is just a normal order product, which we discussed earlier. And then we have these terms here, which now contain just one contraction. So one contraction. And since we have two pairs of creation and annihilation operators, we can have two contractions here. And the only term which gives us something which is different from zero is actually the last term. And the last term, if we are thinking of this as a state which we are creating, this would correspond to actually the anti-symmetrization requirement from the norm of a Slater determinant. So we have two Slater determinants. You can think of this as two Slater determinants for two particles, which should then take the overlap of. This is what that could represent. So just to give you an example, when you look at this quantity here, what you could think of is actually you having to calculate a Slater determinant, which we call 3, 4, the overlap between these Slater determinants here. And then we have the other one, which we just call for 1, 2, and that is the same as A1 and A2 of 0. And then we calculate, what we are doing now is simply to calculate the overlap between these two quantities. So that's essentially what this matrix element here, or this kind of expectation value, or whatever we might call it, represents. Okay? And then the only term which gives us something which is non-zero is actually this term here. And when you do the calculations and put in the Kronecker deltas, this is exactly what you would get if you were to take the overlap between two determinants. Nothing but that. But you see that there's a kind of general trend which we now can generalize into Wick's theorem. So let us state Wick's theorem. So Wick's theorem, and then we're going to prove it. That simply says that if we have now a chain of operators, x, y, z, and we stated it yesterday, so let's just repeat it here. And it's now given, and what you will often see is that instead of writing it like that, we simply just put the chain of operators. So in the literature, you will encounter quite frequently a notation like this, where we just write x, y, z, up to w. So that's just a sloppy notation. What we are doing now is to calculate a vacuum-to-vacuum expectation value. So when you go from the same state to the same state, this is called an expectation value. When you go from one state to another state, we call that a transition probability. And sometimes I will just call them transition matrix elements, because we will often rephrase them in terms of matrices. So this one is now the normal order product of x, y, z of w plus, and now it's the sum over all the one pairs of contractions. So we're just contracting two operators or two strings of operators. And this is normal order. So we would write that x, z up to w, and then we're just contracting one of these. And if you go back to the examples which we had, you see easily that this is what we did in the case of 2 operators, 3 operators, and 4 operators. And this follows all from these manipulations with the anti-commutation rules. And then we have the sum over 2. So this sum here is now the sum over all possible pairings of 2 operators in this string of operators. So we would write this as x, y, z, and all the way up to w. And then we would have something like this. And then this continues all the way up to the number of pairs we have. If we have m operators divided by 2. So if we have an odd number of operators, then this will always be 0. And in this case, we are now contracting all of them. So x, y, z up to w, and we indicate this by these symbols here. So all the operators are contracted. And if we go back to this, so this is essentially Wick's theorem. And the only term which survives is actually the last one. All the other ones are automatically zero because we will always have to normal order some operators. So that means that what we are left with is actually this final term, the sum over all possible contractions. This is the only non-surviving term here. And then you can set up all the Kronecker deltas, and then you will have also specific matrix elements which come into play. So let's try to, before we look at the proof, let's look at an example on how easily we can calculate that. It's always good to look at examples before we take the proof. So let's do an example before the proof. And now we're going to take the two-body operator. So yesterday, we took the one-body operator. So let's take the two-body operator. So we have a interaction term, which we now rewrite as a 1 over 2. So we are summing freely over all the single particle states. There is an integral of alpha, beta, these states, of V of gamma delta. And this is multiplied with the creation and annihilation operators for these specific states. Like that. And now we want to calculate the expectation value for a specific Slater determinant. So we just assume now that we have a determinant which we label as alpha 1, alpha 2, and then we want this explicit expectation value of the interaction piece. And this means that what we have to do then is simply to set up this sum over alpha, beta, gamma, delta. There is a matrix element, which we just leave outside, alpha, beta, V, gamma, delta. So when we perform the contractions, then we know the indices, alpha, beta, and gamma, and delta. And then we can look up in a table, or we can calculate that matrix element. So the most common situation is if you can store all the relevant matrix elements, you would store them and simply look them up in a table. Because then you have defined, when you're done with the contractions, you have defined beta, alpha, gamma, and delta. So what we need to evaluate then is actually this quantity here of alpha 2, A alpha 1, and then I have A alpha, A beta dagger, A delta, A gamma, A alpha 1 dagger, A alpha 2, acting on the vacuum state. Okay. So normally what we do then in all the kind of transcription of the results is simply just to look at the operators. As I said, we will often use a more compact notations. Instead of setting up the vacuum to vacuum expectation value, we would typically just write out the operators and look at the contractions. So the thing we have said now is that all the cases where something is left uncontracted and gets normalized is zero. So the only quantity we need to look at is actually the set of contractions which are non-zero. Now, when you look at this quantity here, we see immediately now by the definition that clearly this one with that one is zero. So internally with the operator, there are only zeros. So if I do contractions like that, so I can contract alpha 1 with alpha 2, so I can do these contractions, but then I'm left with contractions within the operator. So this is by definition zero. This is also by definition zero, because we have a rule which we are using, which simply says that this is the only contraction which is non-zero. So you can set up all possible contractions, but there are going to be many zeros. And there's no point in listing zeros unless you like to collect zeros. it doesn't make much sense, because it sounds like collecting failures, right? So we don't set up all the zeros, but you're free to do that if you want to set up all the contractions. But you have a whole set of them defined by these rules here, which are automagically zero. So that means that when I look at this chain here, there is something which is interesting now. And you will see that if I perform contractions within the operator itself, that gives zero. So it means that I need to connect the operator with something else. This is something which we will use later to define what is called Wick's generalized theorem, which is extremely helpful in generalizing this chain of operators and their respective expectation values or transition probabilities. Okay? So if I want to do this contraction, I get zero. If I want to do this one, I get zero. So everything I try within the two-body operator itself, which is already normal ordered. So this operator is what we call a normal ordered operator. So it has a annihilation to the right and creation operator to the left. Okay. So let's now just write it down. So we have an A alpha 2, an A alpha 1, and then I have an A alpha, A beta, and then I have an A delta, A gamma, and then I have an A alpha 1, and then an A alpha 2 dagger. So I cannot have contractions within the operators themselves. I'm just going to single them out like this. So this is another state. So if I now look at the type of contractions I can obviously perform this one. And I can do that one. That's a pretty obvious one. And that means that if I take this one and that one, and that one and that one, I'm going to get a contribution to the expectation value. If I now go back to the matrix elements, you see now that I have, this is my matrix element here. And now I can put in the right indices, which come from the contractions, which means that now I would have here, I would simply have alpha 1, alpha 2, of V of alpha 1 of alpha 2. So I'm just going to put up here the matrix element which we're having. The matrix element goes like alpha, beta, V, gamma, delta. So that's one possible contraction, okay? So these quantities which we have here, these ones, they're just integrals. And we have assumed that there is a symmetry as well. So if I interchange alpha 1 and alpha 2, that should be the same. Due to the invariance under the permutations of two particles. The next one, which I can do now, I can keep the right hand fixed. So let's keep this fixed. But then I'm going to interchange these two guys. So I let delta act on that one. So when you see